In this video, we're going to introduce our third unsupervised learning technique. Clustering is a great way to, for instance, optimize targeted marketing by identifying customer segments. So in this section, we'll take a look at the key concepts behind and the various approaches that are available to conduct clustering. We will analyze one cluster algorithm in depth to see how it actually works, and we will see how you can evaluate the results of clustering. Lastly, we'll take our approach to the data and apply this to the wholesale customer data that you saw during principal component analysis. Let's take a look at the key concepts behind clustering and what the objectives are. So we will see the various goals that clustering pursues, and we'll also compare clustering and see how it is different from dimensionality reduction that we looked at in the last section. And we'll also take a look at the various approaches that are available to do clustering in practice. So the goal of clustering is to identify similar subgroups, which means that you partition your data set into various groups where the idea is that the members of each groups are more similar to each other, or that the groups are more homogeneous with respect to the features that describe them than any data or any member of any other groups. Typical example is customer segmentation. If you come up with customer segments, then these are groups with certain customers sorted into these groups. And the idea is that those customers inside a group, the members of such a segment, that they are relatively similar to each other, given the features that you have to describe them. And this may be socioeconomic criteria, maybe their purchase behavior, maybe responses to customer satisfaction surveys, but these are customers that are similar, yet at the same time different to others. So here's an example with a very small toy data set. So the result of a clustering algorithm is that you start out with a given number of observations and features to describe them. Here the variables x, y, z, and the output of a clustering algorithm are assignments to a given number of clusters, in this case 3. So each row of the data set is assigned to one of these groupings. And the idea is that the elements that belong to these groups, group 1 for instance, are more similar than any element in group 1 to another element in group 2 for instance. Let's take a look at what this looks like with real data. We are using scikit-learn's makeBlob function from the dataset module to create 250 random points in 2 dimensions. So there are 2 features to describe our data. We will automatically generate 3 different clusters drawn from the normal distribution. We set the standard deviation for each of these clusters to 2. If we do this, then we get an output that looks like this. So we clearly see 3 distinct groupings, but they're not marked as distinct. They're simply in different location of this 2-dimensional space. The goal for the algorithm is to come up ideally with a result like this, which properly identifies that each of this group belongs to a different cluster, as here it was in fact generated by a different distribution. It has to do so without these labels and without being aware of which cluster a data point belongs to, and even without the fact that there are in fact 3 clusters that generated the data to begin with. This is an example in 2 dimensions, and of course we can expand this to 3 dimensions. So now we're going to generate similar data located in 3 dimensions, and this again would be the perspective that you or your algorithm has on the data if you do not know that there were in fact 3 clusters that generated data, or 3 different distributions. And again, the goal would be to get assignments where the algorithm is able to parse apart the membership in these different groupings without knowing that there are 3 or where they are located. We said the first goal is to identify subgroups and assign the data points to those, assuming that we want homogeneous similar subgroups. It is also often useful to simply identify or determine if there are such subgroups in your data. In addition to generating metrics that allow you to identify some partitions in your data or segments, it may also be interesting to find natural hierarchies. And for this, we have a technique called hierarchical clustering, where the idea is that you generate a smaller and reducing number of clusters, starting with the individual data points, and then nesting the clusters so that we constantly merge data points into a cluster that are more similar to each other. So subsequent clusters always contain all the data points that are in a cluster in a previous step. We can also apply this clustering, these clustering goals not only to the observations, but also to the features. So far we talked about the idea that we group the observations according to how they are similar with respect to the features. But we could of course flip this around and look at how similar features are with respect to the various observations that we have on them and create groupings from that. We can even do bi-clustering, which combines these two goals and clusters data by both the observations and the features. And you may remember the cluster map that you saw in the last example on principal component analysis from the Seaborn's library, which allows you to do precisely that. Let's compare cluster analysis and dimensionality reduction. Both of these algorithms, they attempt to simplify and summarize your data so that you arrive at a better representation for the task at hand. They approach this very differently though, because clustering keeps your original data points and it just assigns them to a smaller number of groupings to represent or indicate the similarities between data points. Principal component analysis, in contrast, identifies entirely new features with certain restrictions. The new features should capture as much variance in your data as possible, so they're very useful in describing your data, and they should also be orthogonal to each other. Then you can use your data to represent them as a weighted average of these features using the projection approach and the dot product that we discussed in the last video. The output is also markedly different. So if you compare our clustering approach to for the same data set, then what we would obtain is a projection of our three-dimensional data set, for instance, on a two-dimensional plane defined by the two principal components that we computed here, represented by the red arrows, or as described in the last section. This is useful because it simplifies our data, but it does not identify the clusters themselves. It allows you to inspect it and to explore whether such a structure may in fact be present, but it doesn't identify it directly. So which approaches are there to carry out clustering and actually identify which subgroups may be most representative of your data? There are essentially three different groups. The first are combinatorial algorithms. These essentially attempt to evaluate many different constellations because there are, of course, many ways to combine data points into different groups and then to calculate which of these groupings better accomplish the objective so that the groupings themselves are homogeneous and at the same time different from other groupings. We will explore one of these algorithms in depth in the next videos because k-means is one of those. Another approach is probabilistic modeling. This is based on the idea that we have distributions that generated these the original clusters, similar to the make blocks function that we saw before, that draws data points from different multivariate normal distributions, and then we can estimate which distributions are likely behind these data. So what is the data generating process? An example of this would look like this. So here, for instance, we have again our random data points, and one of these generative models that would estimate a probability distribution does in fact assign a probability to a data point to belong to any of the given of the distributions that it does find. So instead of a hard assignment where a data point is assigned to either of the subgroups, a data point gets probabilities which indicate how likely it is that has been drawn from any of the distributions that the algorithm has generated. Of course, many data points will have very high probability to be in one grouping and zero otherwise, and we can use certain thresholds to assign them to specific clusters, but other clusters will also sit on the border. So it gives a richer type of description of kind of the gray areas between clusters. And the third approach is hierarchical clustering, which builds this nice nested groupings of data points that allow you to decide how many clusters you want, because you get any number starting from the original number of data points down to a single cluster as these clusters successively merge into each other. We will take a closer look at the combinatorial algorithm because it's very popular and fairly straightforward, and leave others for more advanced classes.